Does your company have a product or service that data professionals would benefit from? A BI tool, a cloud solution, or the kind of thing that a data skeptic listener would be interested to learn about? Reach out to advertising at dataskeptic.com. Maybe we can help you bring your message to the audience you're looking for. I'm sorry to play this card because I don't even consider myself that old, but when I was a kid, I had to find weird magazines and try and literally transcribe source code out of the back of them into a computer and hope that by chance the compiler I had used the same syntax and libraries and whatnot as whoever published the code in the magazine had set up. Uphill both ways. I just Googled source code for the game of Go. And shout out to GitHub user Bast, B-A-S-T, a theoretical chemist from Norway, who has made available the source code for the engine of the game of Go. JavaScript, Atwood's Law, of course. You know we got Atwood's Law, so of course it's in JavaScript. Download the zip of this thing, 46 kilobytes. Does everybody appreciate how small a kilobyte is today? Again, I'm not that old, but I started on 5 1/4. Well, I'm really more a 3.5-inch disc guy. I had some 5 1/4s, but what did the 3.5 have? 1.44 megabytes? And for comparison, the entire works of Shakespeare in plain text, ASCII format, 5.8 megabytes. Uncompressed though, compress that, 2.2 megabytes. Still several orders of magnitude bigger than the source code for the game of Go. Now, by the way, we got to put a pin in this. Data Skeptic's going to have to come back to this point and talk about that zip process. If you want to read ahead, you start with Shannon and you run and you don't stop until you get to Kolmogorov of complexity. It's a bit unfair of me to compare Shakespeare and the game of Go in this way. You have to take into account the compiler and whatnot. Needless to say, small source code, incredibly complex emergent system. One of the great feats of computing of modern age, beating Lee Sedol in the game of Go. AlphaZero took up a whole lot more than 64 kilobytes. Complex systems like this are both mathematical and, quite frankly, real and in nature. And while the game of Go might be, invented, contrived if you will, artificial to some, we see equally complex things emerging out of simple systems in nature just as well. Welcome to Data Skeptic Interpretability, a podcast about model interpretability, complex systems, and on special occasions like this, mathematical applications to ecological systems. We're joined today by John Vandermeer, an ecologist doing some really interesting work at the, what I would call, intersection of ecology and mathematics. All that and more right after the break. Thanks to this week's sponsor, the Gartner Data and Analytics Summit. That's being held in Grapevine, Texas this year, March 23rd through 26th, 2020. This is a great event for all types of data professionals. There's a lot of tracks, and I want you to go online to gartner.com/US/data. Just check out the agenda. It's not going to cost you anything. It's worth looking to see if there's anything in the multitude of tracks and sessions they have going on that's of interest to you. There's over 150 sessions, and if you like it, use the code DATASKEPTIC for $350 off the standard price, March 23rd through 26th, 2020 in Grapevine, Texas. So who should attend? Well, analytics and business intelligence leaders, of course. Also senior IT and business leaders, as well as architects. Whether you're currently a chief data officer, if so, there's special stuff for you, or maybe you're on the CDO track. This is a great event for networking, for keeping up with your field, and maybe plotting your next move, whether that be in your career or at the helm of your current organization. I'd like you all to go to gartner.com/US/data and click on Agenda. There you'll find the 8 tracks. My personal favorite, AI, data science, and machine learning. The future starts now. But I definitely want at least some of you in trust and governance and maybe data architecture. Heck, all of these are good tracks. Find the one that's right for you. All that and more at gartner.com/US/data. And use the discount code DATASKEPTIC for $300 off when you sign up. March 23rd through 26th, 2020 in Grapevine, Texas, the Gartner Data and Analytics Summit.
My name is John Vandermeer. I'm in the University of Michigan, Department of Ecology and Evolutionary Biology, and the program in the environment.
Well, John, there's a specific publication I had the pleasure of reading I brought you on to mostly talk about, but before we get into that, can you tell me a little bit about your background? You're not the typical guest we have on Data Skeptic, even though I'm sure people are going to enjoy hearing from you.
Well, my background is basically in biology. I'm an ecologist. I got my PhD in the Department of Biology at the University of Michigan, and I'm now in ecology and evolutionary biology. I've been interested in mathematical applications to ecological systems for quite some time now. My PhD thesis was basically applying Bloch-Volterra differential equations to a laboratory microbiome system.
Very interesting. The title of the paper I read in bioscience was The Community Ecology of Herbivore Regulation in Agro Ecosystem, Lessons from Complex Systems. Well, maybe that's a good place to start. What is an agro ecosystem?
An ecosystem is the sum total of all of the organisms and physical factors that are interacting with one another to create some kind of a structure. And an agro ecosystem is basically the same thing except when it's applied to agricultural systems. Around the world, it's somewhat surprising to people to know that there's a tremendous number of different kinds of agro ecosystems. So, for example, in the American tropics, you can fly over what looks like a tropical rainforest. And if you know something about the forest itself, you can look down and realize that a vast amount of it is actually an agro ecosystem, because when people do agriculture in those kinds of areas, very frequently they'll plant some kind of a crop for 2 or 3 years, and then they'll let the land go fallow. And the land going fallow basically creates a secondary forest, which then matures and becomes something that looks sort of, to the average person, it looks like a regular forest. So vast areas of what people typically think of as tropical rainforests are actually agroecosystems. You have the same situation in a lot of savanna systems where it looks like it's a natural or not a human modified system, but when you stop to look at it carefully, while you realize that various kinds of ungulates are roaming around and tended by humans in one way or another, that's another kind of agro ecosystem. So basically, it's an ecosystem just like any other ecosystem, except as human beings are intervening in it to basically harvest something out of it.
Gotcha. So maybe if you'll permit me, I will say that there are humans engineering that system. And if you're going to engineer it, you'd like to have some model of it. I'm curious to hear your thoughts on how well the models actually describe those systems. Are these high level kind of heuristics, or do we have, at a very mechanical level, a strong understanding of how these systems evolve?
Well, I believe way more on the level of the heuristics. Ecological systems in general are really quite complicated. I'm sure you know. I'm sure your listeners know all that. When you add humans to the situation, why, you're talking about human culture, human economics, human political relationships. So you're just adding a tremendous amount of complexity on top of what is already a very complex system.
Yeah, the complexity part of it is really something that captures my attention because, you have all of these plants and animals and things, they're agents, right? So there's a lot of decision making going on. There's not a simple formula. When the title alludes to the fact that we're going to take some lessons from complex systems, I'd love to hear a little bit more about how you take that process. Some listeners will probably be familiar with complex systems, although if you feel a definition's appropriate, that'd be great. But how do we go from the math book to the agro ecosystem?
Well, the way I like to think about it in terms of ecological systems, at least, the way complex systems fits into it is not, as you alluded to before, in kind of a very, very strict mechanistic way or reductionist kind of fashion, but rather in the simple observation that there's a tremendous amount of pattern that you can easily observe out in nature. For example, if you go to tropical islands, you will always invariably find fewer species of whatever organism you're looking at, fewer species of reptiles and amphibians or fewer species of trees, etc., than you would find on a mainland area. This is a pattern that really holds almost all the time, and everybody knows about that pattern. But when you sit back and ask, where does that pattern come from, that's not quite so obvious why that's the case. Therefore, you have these very complicated systems that sometimes produce patterns that are really quite striking and quite simple. On the other side of the coin, and equally important, you have very, very simple systems that can produce very complicated structures. So, for example, I'm sure you know your readers probably all know the whole bird murmuration kind of thing, where you see blackbirds in the sky that form these incredibly beautiful patterns. And what we realize is that all you need to do, just conceptually, think of a model of a bird that wants to be as close as he or she possibly can be to all the other birds, but also wants everybody else to be away from him or her. And so that little, very, very simple contradiction in terms there creates these beautiful, beautiful patterns at a larger scale. So in sum, you have very complicated systems that produce simple patterns, and then you have very simple systems that create very complicated patterns. Well, my view is that that's the essence of complex systems itself. And it certainly is the case in a very major way for ecological systems.
My background's in computer science, and I tend to read a bit more of that literature than biological literature, but I was very surprised and pleased to see Alan Turing's name come up in your work. Could you talk a little bit about the background of why such a early computer scientist would be interested in these sorts of things?
Alan Turing, had this incredibly brilliant insight, and I would say that brilliance kind of goes beyond the mathematics and the computer science associated with it. It's really kind of a qualitative insight that, when you reflect on it a little bit, it's kind of obvious why. Of course, Alan Turing was the one who mathematically showed that it does occur. That is, you have a system which is, on the one hand, a strongly controlled system where you have, say, two chemicals that are interacting with one another. When one's an activator, the other is a repressor. So the very idea of having an activator and a repressor operating together can be seen as a very stabilizing force. And then if you take that stabilizing force, sort of any kind of activation repressor system in chemistry, if you take that and you put it in a spatial context, say in a petri dish, you would normally think that you put a chemical in a petri dish and it will diffuse out and also reach a stable position itself. So you have another stabilizing force. If you didn't think too much about it, too deeply about it, you would say, well, you have these two stabilizing forces, you put them together, that must be something really, really stable. And of course, what he showed was that depending on how the diffusion rates are coupled together, specifically if the repressor diffuses more rapidly than the activator, what you get is you get an unstable system. You get this patchwork of repressor and activator, which can be really quite permanent in nature. So you have what seems to be a stable system, and by combining the reaction system with the diffusion system, you have this unstable, what's referred to as diffusive instability is what it's frequently called. And that system applies in ecology. I mean, certainly we're not the first ones to point this out. It has been pointed out before, but if you consider the simple idea of a consumer and a resource, or a predator and prey, let's say, the prey item, if it's moving in space, if it's somehow moving in space either through seed dispersal or movement itself, walking around, an animal walking around, why, it's effectively diffusing around the landscape. Predator then comes to attack it, and the predator is also diffusing around the landscape. So the predator is a repressor, in a sense. The prey is the activator, to take the metaphor into the ecological sphere. If those two things are diffusing and the predator is diffusing more rapidly than the prey is, why, you basically have the same underlying mechanism, the same underlying forces that Turing imagined to exist in the chemical system that he was modeling. So ecologists have long realized that predator-prey reaction system, coupled with diffusion or migration, if you like, will create the same kind of spatial patterns, clusters of organisms that Turing saw in his chemical system. And that is what we find. We're not the first ones to point this out.
And what do we leverage from an insight like that? Does it have any predictive power for us?
Well, we think it does. I think it kind of depends on which exact system you're talking about. But if you're talking about a system, for example, of pest control, which is what we were talking about, if you have an organism that kind of dominates the landscape, and in our case, it's a tree nesting ant that dominates the landscape, if it, through the Turing process, creates a pattern so that you have clusters of ant nests and clusters of trees that don't have any ant nests, then whatever agents are associated with the pests in the system are going to obviously be affected by that landscape structure. So the Turing process creates a landscape structure, and it's in that landscape structure that the pests and the controlling agents of the pest really must operate.
I haven't done a lot of work in biology on systems like this, and there's a part of me that looks at it and says, wow, nature's so resilient. One piece of it can fall off and everything will kind of smooth out over time. And then I hear these stories about, a single bad actor species being introduced in an invasive way, and suddenly the ecology is in this chaotic state. And I know this is probably too broad of a question, but in general, how stable are ecosystems? Are they constantly at the brink of potential disaster, or is there some stability we can measure mathematically?
Well, I think the answer to that question is yes and no, by which I mean to say it, of course, depends. There's a couple of different metaphors that people have used in the past to look at the question of how stable ecosystems are. On the one hand, what I call the Spiderweb Metaphor. And you think of a spider web, and the more connections there are in the spider web, why the more steady the spider web seems to be, the more structurally consistent it will be through time, and it'll be permanent through time, the more connections you have. And so that would imply that the more connections, the more ecological connections that you have, the more likely it is that the system will be somehow stable or permanent in time. That's one metaphor. An alternative metaphor is the house of cards metaphor. You build a house out of cards, and the more cards you put into it, why, the more likely it is the whole edifice is going to come crumbling down if you just lose one of the cards. So those two metaphors, I think, have existed in the popular culture about ecology probably ever since at least the last 100 years. They have existed kind of simultaneously in the literature. Now, real ecosystems are neither one nor the other. The popular culture likes to think of the house of cards ecosystem when we're talking about conservation, because we want to conserve all of the species that exist. And so we want to draw people's attention that it's possible, at least, that the ecosystem is like a house of cards, and that we want to preserve everything so that if we won't lose one of the cards and have the whole thing come tumbling down. On the other hand, people are constantly talking about how the stability of an ecosystem is highly dependent on how many actors there are in the system, so that the more actors that you have, the more stable the whole system will be. Early on, Robert May, he published a very influential paper. I believe it was in 1972. I might have the date not exactly correct, but a very influential paper where he took to task the idea of presuming that the more actors you have in the ecosystem, the more stable it's going to be. And he took the simplest equations that he could imagine, the Lacca-Volterra equations, which are the classic equations of ecology, and he basically put them together, and he showed quite convincingly that, as a matter of fact, the larger the system, the more likely it is to be unstable. In a sense, he was sort of moving from the spiderweb analogy to the house of cards analogy, showing that it is not the case that the system will become more stable as you develop more elements connected to one another. Since Robert May's work, which was a basically theoretical work, a lot of people have engaged with that particular topic. And it turns out that there's many complications that enter into it, things that we would refer to as nonlinearities added to the system, basic ideas of network science with connectivity and other sorts of measurements of the degree to which ecosystems are connected together and how that might make them more stable.
Maybe it'd be good to ground our discussion in one of the use cases you mentioned in the article. I imagine the vast majority of our listening audience has some coffee in them at the moment, but might be unaware of the coffee rust disease. Could you share a little bit about it and how maybe, the types of modeling you do could be informative to those farmers in controlling its spread?
Sure. The coffee rust disease is a devastating disease, but it has a curious history associated with it. And that history, we believe that we have developed a sort of conceptual model. And here we're getting very heuristic, I must say. But we believe we developed a sort of heuristic model, conceptual model, which explains how its history came to be. The disease was discovered really by the scientific world, at least, in what used to be called Ceylon, which is what today is Sri Lanka. And this was in the late 19th century. This was on an island that the British had secured Ceylon as a permanent colony for themselves. And they had devised an elaborate system of agriculture, which was, one might today call, a technological package, where they built roads and railroads and various kinds of docks and markets, all associated with coffee. And they basically planted the entire island with coffee. They sort of disrupted all of the natural ecosystems on the island and certainly disrupted any kind of traditional agriculture that would have been on the island. Probably as a consequence of that, these massive monoculture that they had built there was a clear target for any sort of pathogen that would evolve the ability to attack that monoculture. And that's exactly what happened. When the coffee rust arrived in the late 19th century, why it was so devastating, probably wouldn't have been that devastating had the British not decided to create the agro ecosystem that they had created. But nevertheless, it did create a devastating impact, and it caused the British to give up coffee production on the island of Sri Lanka entirely. And that's why you never hear of Ceylon coffee, although it's very popular to drink Ceylon tea in a lot of parts of the world. They switched the crop entirely from coffee to tea. It was at that point that coffee started becoming far more important in Latin America, other places in the world also, in Africa, but our concern here is with Latin America, became really important in Latin America. And of course, with that knowledge of what had happened in South Asia, all coffee producers were extremely concerned about this particular pathogen, which did not exist in the Americas. 1970, 1971, again, the date might not be exactly correct, but around there, why the disease was reported in Brazil. That was the first time. Shortly thereafter, it was reported somewhere in Central America, I believe it was Nicaragua. At that point, then, panic spread throughout the region. In the 70s and the 80s, why there was an incredible amount of effort put into trying to control the disease, not knowing really what they were doing, to be perfectly honest. But there was a lot of just really, really hand-wringing and hair on fire kind of stuff about this disease. Didn't turn out to be much of a problem. Farmers didn't like it, obviously. It did hurt the coffee, but it never was that much of a problem. It became just a sort of constant threat that you had to deal with. Occasionally, a particular farm would have an outbreak, or a particular valley would have an outbreak, but it really wasn't the kind of an epidemic situation that destroyed the entire coffee crop as it did in Sri Lanka previously. Then in 2012, it did. It erupted in 2012. From Mexico to Colombia to Ecuador, it became to Peru, it became a huge problem. And it became a problem even for national politics. I mean, countries like Guatemala, for example, engaged in a tremendous amount of study and worry and concern about the disease. Farmers were losing their lands because their coffee was destroyed, by this disease. Matter of fact, some of the migration that you're still seeing today from Guatemala and El Salvador and Honduras can see the beginnings of the problems in agriculture back in 2012, 2013, where farmers were just simply losing all of their coffee crops. So the question is, why was it so benign for such a long period of time and then suddenly, very, very suddenly, become a problem? You have to understand that the coffee rust is dispersed. It's a fungus, and it's dispersed through spores that are taken by wind in the air. So if you have a lot of movement of air in an area, why, the spores are going to be moving vast distances. Great for the fungus, not so good for the coffee. The way coffee has been produced traditionally in Latin America is under shade. So you have coffee, you don't just have the coffee, but you have the shade trees, those very shade trees that house the ants that I talked about earlier. Those shade trees obviously create a windbreak so that the wind doesn't come screaming through the canopy, bringing all those spores with it. Now, what happened throughout the 70s and the 80s, all throughout Latin America, from Mexico to Peru, you had this ongoing deforestation that was happening. It was the popular culture knows about the deforestation of the tropical rainforest, which was an ongoing project, as we all know, but also at the same time was a deforestation of the traditional coffee farms. Traditional coffee farms, as I mentioned, they had shade associated with them. Many of them actually appeared to be, you look at it from an aerial photograph, they just appeared to be a forest. But as that deforestation was proceeding, why, the winds started moving more and more. And as the winds started moving more and more, that created a totally different regime. Basically, the parameters of the disease actually changed because of something that happened at the landscape level, that is the deforestation at the landscape level. And effectively what happened is you hit a tipping point in 2012. So we had what we referred to in the article as a critical transition at some point where the spore load in the air just became so high due to the continual deforestation that was going on, probably over a 20-year period. That is our explanation why the coffee rust disease became such a huge problem. And I think it's pretty clear, I hope it's clear to your listeners, how that's a classic example of the application of principles of complex systems.
So when I think about ecology at a very naive level, it seems like we could think, all right, it's like that old song, the lady who swallowed the fly and swallows the spider to swallow the fly, and all I need to know is who eats who. What beyond who eats who helps really tell us the story of what's going on in the ecology?
Well, maybe who eats who is not the very best way to look at it. Is who does what to whom and with what, and probably would be the best. You have the fungus that attacks the coffee, for example. But as we point out in the article, why, you also have other things that attack the fungus. And then you have things that attack those things that attack the fungus. I mean, the very structure of the ecosystem that we talked about in that article really wouldn't even exist if it wasn't for the case that there was a fly parasite that attacks the main ant that's creating the spatial pattern in that structure. That fly that attacks the ant doesn't really affect the ant so much by eating it, although it does eat it. Basically, it's a parasite, right? But it actually changes the behavior of the ant. So that when the fly comes along, why, the ant begins a process of either running back to its nest or going into a catatonic state so that the fly basically can't see it. When the ant goes into this catatonic state so that the fly can't see it, why, it ceases in the various activities that it engages in, which keep the ecosystem together. For example, the one thing that we pointed out there was the green coffee scale, which is actually a pest of the coffee. By affecting the behavior of the ant, not consuming it, but by affecting its behavior, what it basically changes one of the parameters in the rules that guide the way the ant deals with the other organisms in the system. So, for example, if you have predator prey equations that will indicate how the ant preys on one of the other herbivores in the system, so the ant, for example, the ant will eat one of the other herbivores or pests in the system. And when the fly comes along, what the fly does is the fly interferes with the ant's ability to do that. So the fly effectively creates a nonlinear effect on one of the parameters of the interaction between the ant and this prey item that it's trying to eat. That kind of nonlinearity, that really changes the way ecosystems are put together. There's a recent, really, really nice article showing how if you take and you sort of create a daisy chain of these kinds of indirect interactions, what we refer to in our article as trait-mediated indirect interactions, you take and you daisy chain them so that you have cascades of indirect interactions. It's actually those cascades that provide some of the scaffolding of the network, the ecological network, that actually creates the stability or the persistence, let's say, of the ecosystem. So it's not just who eats whom, but it's really who eats whom plus how do they do it? How do they affect other things that do it? How are other things in the system affecting them?
Yeah, and the presence of those effects, like the behavior change in the ant, as you'd mentioned, they introduce these nonlinear effects, which for a mathematician is either a joy or a nightmare, depending on how you want to look at it, because that problem is going to be a hard problem, right? Do you see that a trend in more computational biology is going to be taking off? Have we not had the computing power to do this, or not the models? Or I guess, what do you think the future of research is going to look like?
Oh, that's really an excellent question that I'm not sure that I have a lot of insight into it. I mean, on the one hand, I acknowledge that the kind of power that we have right now is really immense. And it's very seductive for people who do the kind of work that I do because I immediately realize how incredibly complicated the systems are that I work with. The joy of analytical solutions escapes from my life many, many years ago. And so we don't even think about that any longer. But there are other ways also of thinking about complex systems other than either the analytical solution or the brute force simulation. I mean, there are ways of looking at ecosystems in a qualitative way, as you mentioned earlier, the heuristics of it. There are ways of looking at qualitative behavior, also supported by mathematical models, don't get me wrong. But there really is a long history of qualitative mathematics, or mathematics used for what I refer to as used for educating the intuition. So you develop mathematical models, not necessarily for predicting what's going to happen, but mathematical models that enable you to develop your own internal heuristics about the way a system is working. So, for example, as we discuss in the article, the question of how that green scale insect, which is one of the pests of the coffee, how that actually operates. Yes, there's a mathematical model associated with it, and the mathematical model shows how there should be a critical transition. It even shows things like there should be these strange things like basin boundary collisions leading to chaos and things like that. And all of those things can be shown analytically with very simple models, for sure, but they also give insights into the qualitative nature of the system. I don't think this is all that new, really. I mean, forgive me if this is too simple-minded, but I mean, when Newton talked about the theory of gravity, yes, he had an equation that was very, very highly predictive, but there's a really famous quote of his, or a famous narrative of his in the Principia, where he talks about shooting a cannonball and how the cannonball can be shot harder and harder such that it will just go around the Earth. And doesn't that look just like the planets? And, it was the sort of the qualitative insight that matters as much as the equations that were there. And who can forget Albert Einstein asking what seemed like a foolish question perhaps at the time, but what would the world look like if I sat on the edge of a lightning bolt? Those are the kinds of questions that I enjoy asking about ecosystems, and I enjoy utilizing mathematics to try and gain qualitative insights into how those things operate.
I am certainly not a farmer, as my next question will make very obvious. I think if I were to try and grow something, I'd have an attitude of like, okay, kill all the pests, get rid of everything except what I'm trying to grow, so on and so forth. Yet some of those simple heuristics that you mentioned in the paper, like avoid monocultures and don't poison your natural enemies, these are like almost great fortune cookie wisdom. How does the farming community absorb things like that? I imagine they might not be up on the latest in complex systems. How do you get your work to help people in the fields?
I'm asked that question all the time, and I never really have a good answer to that. The answer that makes the most sense to me is to look at the medical profession. Look at the way medicine was practiced a couple of hundred years ago. I mean, you got sick, and what did the doctor recommend to you? Leeches or bleeding or rain dances or whatever. Some of those heuristics perhaps made sense. The doctor would also tell you to eat well, stay healthy. That makes sense too. There's no question about it. But the kind of things we do in modern medicine today are based on a fundamental understanding of fundamental sciences like physiology, for example. We no longer bleed people when they have a fever because we understand what the physiology of the fever is all about. And we treat it with the understanding that comes from our understanding of physiology and the various other sciences that go into the modern medical field. I feel the same way about agriculture. The way agriculture has developed has been more or less in the direction that I'm advocating for ever since perhaps 10,000 years ago when people first started doing it, up until World War II, basically. It was at the end of World War II that we had the massive modification of the way agriculture was done, mainly for the purpose of creating profits, not for the purpose of producing food. So we have to do monocultures to accommodate the machines that we put out there. We have to flatten the land and flatten the landscape in order to accommodate the pesticides that we have to produce, we have to use, et cetera, et cetera. For all practical purposes, since World War II, agricultural technology has been based on the sciences of chemistry and mechanical engineering. What I'm proposing, what people like me are proposing, I should say, is that we base progress in agriculture on the science of ecology as opposed to the science of chemistry and mechanical engineering. And we look at the system in the same way that the medical world would look at the science of physiology. Yes, we can't really say what the farmer should actually do when faced with these problems that he or she is faced with. But, the same thing was true back in the 19th century before we understood things about plant nutrition and soil biology and things like that. So as we develop more sophisticated understanding, and from my point of view, that sophisticated understanding is going to come through some of the ideas associated with complex systems. As we develop more sophisticated understandings, we will, just like happened in the medical field, we will be able to tell the farmers what they might be able to do to make things better. I know that's not necessarily the best answer to that question, but it's the one that makes most sense to me, at least.
Part of what appeals to me about that perspective is that it seems that you get a layer of interpretability that maybe some of those more chemistry type approaches wouldn't. The paper discusses a lot about shade cover and that sort of impact, and I, as an outside reader, can immediately kind of grok why that's important and see why it would be in your model. Whereas if I had read a paper about the balance of this chemical to that chemical, I don't know that I would have gotten much out of it myself. Do you think that interpretability is, maybe it's not the primary factor, but would you agree that's kind of something you get for free along the way in your approach?
I think so, yeah. I think it's a good way of putting it. Perhaps I should have put it that way. Maybe at my next podcast I will.
Well, usually at this point, I like to ask people if there's anything you think I should have asked that I haven't.
One of the things that I am asked frequently is this conundrum that we always face when we're talking about applying ecology to anything, and that is the idea of trade-offs. If you want to do one thing, you sacrifice something else. To what extent do these so-called trade-offs have anything to do with complex systems? And I think in trying to understand the way agro ecosystems work from the point of view of thinking about what the farmer really needs, we frequently encounter things that appear to be contradictory, things that appear to be, if you do one thing good, why some other bad thing is going to happen. What are those trade-offs between these various things? So, for example, I'm in Puerto Rico right now, and we're working in coffee agro ecosystems. The article didn't talk about that, but that's one of the projects that we have. And so we have here, right across the street from where I'm talking to you right now, as a matter of fact, it's a farm. And on that farm, there's a very, very tiny ant that stings like crazy, sometimes called the electric ant. And what happens is when the coffee is ready to harvest, why the workers that come to harvest the coffee, when they come to a little patch where that ant lives, why they just skip it. They don't harvest the coffee because the ant stings too much and they really hate it. So it sounds like the ant's a pretty bad thing, right? But it turns out that one of the worst pests that we have here in Puerto Rico is the coffee berry borer, just like it is in Mexico. And it turns out that this ant is a very, very effective predator against the coffee berry borer. So what is the farmer to do? I don't have an answer to this question, by the way. So let me just tell you, I don't have an answer to it. But the point is, it's a very, very clear case where there's a major contradiction. Should we be looking to this ant as we are now doing research on this ant, should we be looking to this species of ant to promote it so that it controls one of the major pests in the system? Or should we be looking at it as a pest itself because it interferes with the harvesting activities of the workers in the system? That's the conundrum of a trade-off when we're dealing with agroecosystems.
Yeah, that's very interesting. The science can describe both situations, but not really say which one is quote unquote right, I suppose. How does a decision like that ultimately get made then? Is it up to farmers to decide?
Well, it's always up to the farmers to decide. And what we're hoping with our research is that we're hoping we're going to understand exactly how that ant works within the context of its full ecological environment. And obviously, the best thing to do would be to somehow manage the system such that the ant goes away when the workers are there and comes back when the pest is there. That's kind of a no-brainer to say that you should do something like that. Well, can you do that? Well, we have no idea how that can be done right now, but I have a tremendous amount of faith that knowledge about the ecology of the system will ultimately provide us with the way in which we could plan the development of an agroecosystem such that the ant will be there when you need it, but won't be there when you don't want it.
Would it be fair then to almost describe those ants as technology at that point?
Yeah, I suppose so. That'd be okay with me.
Well, John, this has been really interesting. To wind up, where can people follow your work online?
Well, you can go to my webpage at the University of Michigan. Most of our stuff is listed there. There was a couple of sort of promotional pieces that the University of Michigan did a couple of years ago that might link to also. I can send those to you, but they came down to Mexico and did a bunch of filming, and they put together a little, I would call it a promotional piece for our project.
Excellent. Well, I'll have that and some other links in the show notes, including the bioscience article. Thank you so much for coming on and sharing your work. Thanks for listening to Data Skeptic. Our guest today was John Vandermeer. Our theme song is Number 5 by Big D and the Kids Table. Claudia Armbruster is our associate producer, Vanessa Burciaga is our guest coordinator, and I've been your host, Kyle Polich.